So this talk is about Python inside the virtual machine and how that actually affects Python as a language. And because there's a lot of potentially boring stuff in there, I would really welcome if people would just ask questions or anything of that sort along the way to spice it up a little bit. What's interesting about, I think, Python as a language is that we all use it, and we like it, I think, for the most part. At least people don't seem to mind it too much. But it's actually surprising how nitty-gritty the interpreter internally is and how much it sort of restricts us in what we can do, but also how much it enables us in other ways. So this is basically, so I should give a little preface for this. I've been doing Python since, so the first version of Python I used was 2.0, but it wasn't, like I wasn't programming when 2.0 came out. I think the first one I actually used was 2.2, but I had an interest in trying to figure out how it goes back to see how the language evolved and how the interpreter evolved. And then just recently, I think last year I already gave a talk similar to this one, and for that one I decided to see how it is to compile Python 1.3, I think. So it's interesting how far you can go back with the Python interpreter and actually still get a running binary out of it. You can actually still compile the old versions on modern computers and see how the language evolved. And so there's a lot of stuff in the interpreter which didn't really change over the years. And I had just an interest for it because I like Python as a language. I spent a lot of time working in it. I have made many open source projects in it. And as such, I was always curious to see how far you can take the language and how you can evolve the interpreter. Or in this case, how you can't really change all that much because of some reasons, which we'll go into. My day job at the moment is I work for the most part on Sentry, which is an open source project written in Python, mostly based on Django framework, and it's an error reporting tool. And then other than that, I did the Flask framework. I started a new sort of static file content management system recently called Lector. And I have lots of Python libraries like Werkzeug, Jinja, Markup Safe, and many more. So I have done a lot of Python, but never really as a core developer on the language. I do have commit access for some inexplicable reasons, but I barely ever contributed anything to the interpreter. But I have a lot of fun looking in and see how the interpreter is. So I would say that in regards to all of the languages which exist in the world for programming, they kind of are on a line that goes from very dynamic to very static. And very dynamic can be seen in many different ways. So for instance, how many here use Ruby or have used Ruby a little bit? Okay, not that many, but I should probably explain a little bit about Ruby because it's kind of interesting in a comparison to Python, which is that in Ruby, they pride themselves as the Ruby community that it's a very, very highly dynamic language in the sense that you can change a method on the, on the float class, and then you can change addition to subtraction. Not that you would do that, but you can do it. So it's very dynamic in the sense that you can change behavior which you think shouldn't necessarily be something that you want to change. And Python doesn't do that. You can't change the under-add method on the float class. I mean, technically, I guess you could, but it was never designed to support that. But I actually think that Python as a language is way more dynamic and as a result, way harder to optimize than it is to optimize Ruby. And have some examples of this. And I find it interesting because we all are being told that Python works in a certain way. And then as you dig deeper and deeper into it, you realize that that's actually totally not how the language works. And you would think that, oh, maybe we change the language so that it works how we are told that the language works. And then you realize you can't do that because people actually depend in very bizarre ways on some of the internals in the language. And as a result, it makes it very hard to evolve the language. So certain things that people want to have for a long time is getting rid of the global interpreter lock. That turns out to be hard and also very much relevant to how the interpreter was designed initially and what guarantees it gives. It is very hard to not just bring concurrency into the language, but also to bring the ability to have multiple versions of the same library loaded at the same time. It makes it very tricky to have multiple interpreters running in the same executable side by side without sharing anything in it. And it makes it even harder to just change some of the basic principles in how the types in Python work. Over the years, more and more stuff has been piled on top of this already very complex language. In particular, Python 3, I think, goes very far in doing all kinds of stuff on top of all of this, which also lacks a little bit of peer review, I would say. OK, so this is the language we are all told exists. You have a global variable called magic. It's 42. And there's a function called addMagic, and it adds a plus magic. I think that makes a lot of sense. It's not a very useful function, but it is a function that everybody understands. And a lot of tutorials on the internet will tell you that this is actually equivalent to this, which it's not really. It's not really for many different reasons, but in fact, it is totally not that. What is actually happening behind the scenes is that Python compiles all of this into bytecode, and the instruction for adding things together is called binary add. And from that moment on, we go down a rabbit hole which has nothing to do with under, add, under. There's a file in Python called Ceval, which is I don't know how large it is at this point, but it's very huge. I think it's about a couple thousand lines. And it's basically a huge switch statement. And it's a big loop, and it checks every single opcode. So for instance, there's a branch in there for binary addition. And I cut this tremendously. In fact, there's a ... All of those I just deleted entirely from the slides because they're not super relevant. But if you actually consider how much code the interpreter has to walk through to add two numbers together, it's a lot. And it became bigger and bigger over the years. It might have been easier at one point, but at the moment, it takes two arguments from the stack. So it pops these two arguments, and then it does all kinds of stuff. For instance, it checks if both of those if the first variable and the second variable, or the first argument, the second argument, if they're both exactly integers and not just subclasses or anything of that sort, then it does a special thing. If both of them are exactly strings, then it does a special thing. Otherwise, it goes to PyNumberAdd. I will look into what PyNumberAdd is. But what do you think PyNumberAdd should be with that name? It implies something with numbers and addition. If you actually look at what it does, there is a thing in there where the first part has something to do with nb_add. That's number addition slot. We'll go into this. But then also, it has a special handling for sequences in there. So PyNumberAdd is not actually anything to do with numbers. It's actually PyObjectAdd. It just has a bad name. But one thing you will notice here, there is no under_add anywhere in this function. Like, it doesn't look for an attribute called under_add. What it does, it invokes this binary operation 1 on the variable v and w. That's the first two arguments to the number add thing. And then it looks at the slot nb_add. So how many here know what the slot is in Python? OK, so I will just go by random. One person over there who just said slot. Actually, let's do it differently. Slots in Python are two things. And a lot of people think that slots are under slots, under, to give an object what's called a slot and to remove the dictionary. That's one of the two slots that Python has. The other slot that Python has is these special things which are added on top of the type on the C interpreter to not have to look into a dictionary attribute. What this means in practice is that up here on the V and the W object, which we have on the interpreter level, there are special containers. It's a huge struct, and on different positions in the struct, there are different methods stored. So for instance, if you add two numbers together, it's ridiculously hard to read. We're just going to skip past this as much as we can. But there's each variable, each Python object has an OB type, which is sort of a pointer to the type object it has. And on OB type, we have, for instance, TPS number, which means if the type is seen as number, there is a huge list of methods it could have. And then in this case, we might invoke that thing. And then otherwise, if what do we have? So we look at the slots of both two different types, and then depending on the relationship of them together, we add numbers. And this actually, if you wouldn't look at my slides, is in total something like 400 lines of code for just adding numbers together. And where is underscore, underscore, add, underscore, underscore? It doesn't appear anywhere. Sort of, that's the big lie. The big lie is that we are invoking these special things, but we're not. Instead, we're looking at these stupid slots things. And they're surprisingly frustrating, I would say, if you look at the interpreter and try to reason about it. It would be very nice to say, like, you have an object A and an object B, and to do something, an addition with them, or a subtraction or multiplication, there's a very, very clear thing that happens. JavaScript learned this recently. They have a standard, and it defines very clearly what happens if you add two objects together. In Python, it's impossible to tell. It depends, especially if you have Python 2, it depends on flags on the object. It depends on the specific relationship the types have together with each other. And I would argue that there is probably not a single programmer in the Python community who could tell you exactly what happens if you add two objects together. And I kind of assume this from the fact that there is the PyPy project, and the PyPy project tries to implement the Python language in Python. And it's kind of interesting sometimes when PyPy disagrees with the implementation that CPython has, and you would think that they must get it right, but then they still disagree in certain ways. And it is very tricky. So to make this a little bit more concrete, what is a slot? A slot is basically it's a slot on a struct, which the Python interpreter keeps for every single type. So you can imagine this way. You have an integer. And if you look at the class from the Python side, there's a dictionary on it. And in this dictionary, there's special underscore, underscore, add, underscore, underscore. And there's a function to it. So there's a function that is invoked with that name. But the C interpreter was written long before, I guess, these special methods existed. So when you go back to, I don't know, 1995, there were two things. There were Python classes and there were C types, and they had no relationship with each other. So if you added two integers together that were written in C, that were like built-in types into the language, then it always invoked this special slot method called nbadd. That's what it did. And later on, they added support for classes, and then I said, okay, so it would be nice if classes could be also added together. So they added independently of these C types, they added Python classes. And in the Python class, the logic was underscore, underscore, add, underscore, underscore is the special callback method to add numbers together. And so they had these two separate systems, and they tried to unify them, I guess. Or maybe that even happened side by side. I can't really tell. It's hard to say. But nowadays, what happens is if you have a C class and it has a slot, then there is some magic in the C code which exposes these slots as these special methods to Python code. And same way, if you make a special Python class with underscore, underscore, add, underscore, underscore, it takes this function which is there and stuffs it into the C type and stores it there as a C function. So they try to synchronize up with each other. So you could think that foo underscore underscore add underscore underscore can be this foo type TPS number nbadd, which we have on the C interpreter. That's sort of the expectation that they are synchronized with each other. But history makes this really hard. So for instance, you have to imagine that very early on Python had integers and floats, but it also had strings and lists and tuples. And so that's what probably Guido wrote this himself. He decided that there are two different concepts for adding things together. One for numbers, one for sequences. And so they have the two different slots for adding things together. And plus looks at both of those slots. So you can already see that there might be desynchronization that can happen. But theoretically, they're kind of supposed to map to underscore underscore add. But it just becomes very hard to explain as to a user. And that's also why I guess nobody really explains that, because it seems irrelevant for the most part. if you read a tutorial, it says a plus b is a under add under b. Slightly more correct tutorials have discovered that what seems to be happening is actually the type of a invokes under add with, I should actually say, a comma b. But both of them are wrong, because here's what happens if you write a plus b in the interpreter. It checks if a and b are integers. In case they're integers, it tries to do a fast addition on the, in a very special place in the interpreter. If they are both strings, then it tries to make a fast concatenation. Then it will try to do a number addition. Is A implementing number slots, then it resolves the slot. Is B implementing number slots and resolves that slot? Based on the type relationship between them, which is very complex, I'm not going to go into this, it invokes them slightly differently, but usually it ends up with something like the slot of A invokes with A and B. But then if that also doesn't work, then it tries to do the sequence concatenation, which goes through a different interpreter path. In comparison, this is what happens if you do a dot under add under b. It looks for an attribute called, first it looks for an attribute called under add on type, then it looks this up and invokes it. The scary thing is this thing is easier than this thing. So the fast path that we have in the interpreter through the slots and everything we have at this point is significantly more complex than what we are actually told as Python programmers what happens. This path is not optimized. This path is often not directly invoked, but you can find places where manually writing this is actually faster than this. Not always, but in some cases. And the reason why I want to mention this is because the interpreter has grown over the years with optimizations and other things to make it operate faster in this very complex world it has set up. And you would think that, well, why don't we just take this thing and optimize it and then say, when you do a plus b, it does a under add under b. Like, why don't we just do that? That seems to be like the reasonable thing to do. That's easy. That's what every tutorial says. Why do we do this complex thing? And the reason for this is that, unfortunately, we expose so much of the language to the ecosystem around it that we can't change the interpreter anymore. So everyone who has ever written a C extension in Python is quite aware of how low level the C API is. So every custom C type you add knows about the slots. Even if you ignore the C API entirely, slot wrappers as a concept are exposed to Python as a language. Every once in a while, even newbies that have never used the language encounter an exception message which says like, slot wrapper has no attribute under foo or something. Because all of those internals need to be exposed to the runtime. And we have this, I would say, very, very complex just language buildup, which is hard to explain to people. And it's sort of, for some inexplicable reasons, used by everyone with all of those little nitty details. So for instance, I have a better example later on where we have some code for this. But point is that they are not equal. And they try to be hidden for you as a user as much as possible. So for instance, if you have a class X, which is a subclass of object, I think most people have written this at one point to add the special add method. And then when you access this, you can see there's an unbound method X, which happens to be a lambda. What happens if you look at what a C type looks like? Well, if you do it under add on the C type, then you get a slot wrapper. What's a slot wrapper? Well, what this actually is, this is a special thing which wraps a C function on the C interpreter level. But it's exposed to a Python user. Like, you can see that these are clearly not equivalent, even though they should be. And so we have exposed all of this like very nitty-gritty detail of the interpreter all the way up to the Python language. So if someone ever changes this behavior, all the Python code would have to deal with a different object there. And this is something that unfortunately Python didn't do just as well as JavaScript, for instance, because in JavaScript, everything is a function. Like there is no difference. We have one function in JavaScript, and if you write one yourself or if you do it on the C level, they're just the same. There's no real difference in looking at them, other than that one of them might not expose the source code that created it. Whereas in Python, we have slot wrappers, we have method descriptors, we have built-in function, we have callable objects, we have a huge range of all of those, and they're all exposed to slightly small details in how they behave differently. To give you an example, if you have an unbound method under, add, under, and you take a reference to it and you put it onto another class, then it acts as a descriptor, so it receives self as the first argument. If you try to do the same thing with a slot wrapper, it doesn't do it. And people start depending on this. So for instance, one thing I have seen a couple of times is that someone writes a class, and then as a class attribute, there is written conversion function equals int. And that depends on int, the type not having a descriptor, so not binding self as the argument. So you could never change that behavior. You could never clean it up because we depend on these little differences in it. And as you go into like PyPy as a language, they all have to replicate every single bits and piece of these like very intricate parts. And Python tries to sync them up as much as possible to hide this complexity as much as possible from you, but it unfortunately doesn't get it right all the time. And the reason why we should care about this is because it's very complex and everybody uses it. And it makes optimizations almost impossible. We have to emulate it as we go to other languages. But it also shapes how our own code works. And this is an example which thankfully has been fixed, but this is, I think, a very interesting one. There's a module called RE. So if you run this on Python 2.7 or newer, it behaves differently. But I think it shows very well in how weird it gets. So there's a module called RE for regular expressions in Python. And if you compile an expression, you get an object back. And that object is a special object called SRE rule or SRE regex or something. And if you access under class under, it gives you an attribute error. That seems weird. Like, why does it do that? How does it do that? How does it make any sense for an object in Python not to have a class attribute? And in fact, it also doesn't have under wrapper under. So it has a whole bunch of behavior of a normal Python object, but then also it never responded to those special attributes. So how can this be? And the reason for this is that this object was written in C, and whoever wrote the C object customized the entire behavior of sort of how it looks like in the Python land. So the C interpreter sees a different version of this object than Python code would do. So for instance, if you would want to write the wrapper function in Python to invoke the special under wrapper under function, you could never implement this because at least this object would always disagree with it, because you can only access the class information and the wrapper information from the C language. You can't do it from the Python language. And it gets really weird because there are so many cases of this. And this is an example of where the C API allows you to implement a certain behavior that is completely invisible from the Python level. So this obviously is not Python 3 code. This is Python 2.4 code, let's say. And in older versions of Python, it was possible to create a class that is not a new style class, so to say, where you implement under get attr, and then it returns an attribute from another object and would pass through all of the special methods. So you could, for instance, instantiate A, and it looks like 42, because when the interpreter looks for the under wrapper under function, it goes and looks through get attribute, and it will find the under function on the integer 42. So it is a 100% proxy, so to say. And modern Python doesn't work like this anymore. And the reason for this is that this special instant type, which exists in all the Python versions and in old style classes in newer Python versions, forwards all of the calls like it did in very old versions of Python. So it emulates what the Python interpreter used to be at one point. just that at this point, it has to do it as this very complex proxy object. So when you actually consider how Python as a language was taught to people, at one point, this under, at, under was actually correct. It just became more complex over the years and now has this massive sort of disagreement in how it works. The other thing that sort of leaks through, which is a little bit easier to understand, is Unicode. And I think for Unicode, it is kind of important to understand where the language comes from. When Python was created originally, it didn't have any Unicode support at all. It had strings. And strings were implemented as straightforward as you can imagine. They hold a sequence of characters. Each character has a numeric value from 1 to 256. And because of that, it gives you certain ideas of how a string is supposed to work. And Python exposed this. So for instance, if you have a string of ASCII characters, you can always get the first character. You can always get the second character, the third character, fourth. It's very easy to access these individual characters on it. When they started adding Unicode support to it, they decided that the best way to do it would be to mimic this behavior. But instead of going from 0 to 256, they would go from 0 to 65,000. And then later on, when they realized that Unicode is going to grow, they decided that we can also compile Python in a version where it will go to much larger numbers. And this is nice on the one hand, but it's also very disappointing on the other. So does anyone here know what UCS means? It's an encoding. UCS, I don't actually know what it stands for. I think it might be Unicode something system. It was basically, about 25 years ago, I guess, someone decided that we need to evolve ASCII for all the languages in the world. And there were two independent consortiums which decided to do that. One of them was the Unicode consortium, and they decided 65,000 characters is enough for everyone. They were wrong. They had to make it larger afterwards. But independently, there was a group of people on the ISO committee which decided that they're going to make 2 to the power of 32 different characters. And they made a much more complex standard, which didn't really go anywhere because they couldn't figure out how to encode it efficiently. And then along the way, while these two standards were evolving, two things happened. The first one was that people realized Unicode will have to get more characters than 65,000. So in particular, if you use emojis, emojis are way past 65,000. They need more than 2 bytes. But also, eventually they realized that it's actually very valuable to encode the Unicode data into more compact encodings. So if you imagine that you have most of your text fit into ASCII or Cyrillic or something that's very low in numbers, then it doesn't really make any sense to store all the numbers with a lot of zeros in between because that's just a waste of space. So if you would store all the text in 2 bytes, then first of all, you could only store 65,000 individual characters per position, but also it would be very wasteful. So the UTF-8 is the most common encoding where you can sort of make the individual character larger or bigger depending on how large the number in it is. So ASCII, for instance, fits into 8 bits. Cyrillic, I think, fits into 2, if I'm not mistaken. And it grows up like this. UCS2, on the other hand, is basically the original Unicode encoding. It's each character going from 0 to 65,000. And there is no support whatsoever to encode characters in it which are larger than 65,000. So if you take a standard Python 2 interpreter and it's compiled with UCS2, then accessing the first character, second, fourth, and so forth will give you exactly the character. But then if you encounter an emoji, the emoji will split in half. So if you would have to access the first part and the second part of the emoji independently. And so if you want to deal with emojis in Python 2, you would have to compile it with UCS4, which takes then 4 bytes per character, which is enormous waste. In particular, it's an enormous waste because the largest character which can ever be in Unicode is only 21 bits, I think. Yeah, 21 bits, which is just slightly above half of it. So you will have the vast majority of your space unused. And so why do we waste so much memory in Python? Why do we not just use UTF-8 or something like this? Because we guaranteed that if you access the first character, you will get the first character. And if you access the second character, you will get the second character. And the only way to do this in UTF-8 would be to scan character by character by character to figure out which one you want to access. Whereas if we store it in UCS2 or UCS4, then we can skip the number of bytes until where the character is. And there are many arguments to be made about a system like this versus other systems, but I would say in the last 10 years it has emerged that UTF-8 is the way to go. And a lot of newer languages actually embrace this a little bit. So for instance, Go is UTF everywhere, and it doesn't give you character access. Same thing with Rust. I think Swift might be doing something similar, but at the very least, Apple never really gave you this direct access to characters. So the language didn't give you this idea that you could do this efficiently. And it's kind of disappointing that in Python the nice thing is we fixed this in Python 3 a little bit, where depending on the largest character in a string, it gets bigger or smaller. But it still gives you this guarantee. And this guarantee is only given to you because the interpreter decided at one point that that is a reasonable thing to do. It was not, I don't think there was a conscious decision in doing this. I think it just happened. And this is sort of a general story in Python where the language that we use is pretty much exactly the interpreter as it exists. And this, on the one hand, makes it very hard to do optimizations. And it can get really weird if it desynchronizes, but it doesn't happen very often. But on the other hand, it gave us, as Python programmers, I would say, a very different way to look at the language compared to many other programmers. If you're a JavaScript programmer, or if you are a Ruby, well, maybe not Ruby, but if you're a JavaScript programmer at the very least, you take the language and you use it, and you live with the limitations of it. And maybe over the years you realize that there are so many limitations in it, and you go to browser vendors and ask them to give you a little bit more access to the language, but it stays very high level. It stays very sandboxed and contained. Whereas in Python, because the interpreter has always shined through so directly, a whole bunch of stuff has happened, which I think is quite unique. The first one is, and I think that's, for me, the biggest reason why I like Python so much. Like, even though I know that all of this exposed interpreter makes it hard for us to ever get rid of the GIL, makes it hard for us to ever do certain optimizations, we were always kind of locked into this sort of language that works in this way. But on the other hand, we have so much power in our hand because we have access to the interpreter. This is, like, who uses SysGetFrame or has heard of it? A shocking small amount of people. SysGetFrame is sort of the secret sauce of what makes a lot of Python code spicy. I wouldn't say good, but basically what you can do at any point in time, you can ask the interpreter to give you the internal state of the current call site. And this returns a frame object. And this frame object exposes almost the entire interpreter state at this point in time, which from a performance point of view is nuts. You shouldn't do that. Like, if you would go into like designing a new high-level language, everybody would argue that this never give this thing. This thing is slow, it's ridiculous, like, just don't expose it. It shouldn't exist. Python exposed it very, very early on, and Code started using it a lot. And because Code started using it, the core language developers were forced to keep it at least somewhat performant. And something like SysGetFrame also exists in other languages like Ruby, and in Ruby it's really, really slow because nobody uses it. So to understand what SysGetFrame is, it gives you a frame object. And with the frame object, you can access everything that's there. So for instance, you can access local variables. You can, under some circumstances, change local variables. You can see the file name where you're currently executing. You can see what exception has been on this frame and so forth. And this has been abused, but also heavily used. So for instance, there's a project called SOAP interface, where you call a method called implements, and it goes into, it looks at the current call site, and then goes one up, and then it asks the class to inject a new attribute into it. This is something that doesn't make any sense from a calling point of view, but they just decided to do that. The warnings module, depending on where you call it, will anchor the warning to a different code location. So for instance, you can say, I want to warn that this method is going to be deprecated, but I want the warning to be relevant 2 frames up. And it does this sort of stuff. The inspect module is full of this stuff. Logging, for instance, will skip frames in the logging module so that it logs based on the location where you invoke the method yourself and not where the method was defined. And then like so much debug support. So for instance, does anyone know twisted manhole? Probably not. It's one person. It's a very uncommon thing, but there are so many versions of this that people use inside companies even, where you can take a running Python interpreter and it just runs there and it does its thing, and then something weird happens in it. Let's say you have a computer game and it just has a server process, it runs there, it emulates a game world, and you don't want to stop it, but it misbehaves slightly. You can actually attach a debugger to the Python interpreter and execute Python code running in there and figure out what it does at any point in time. It gives you all this state of the interpreter, and you can do really interesting things with it. So for instance, I work for Sentry, and Sentry is a system where you can report crashes to. And we get all of this information out of a crash at runtime from the interpreter. So we cannot just report where the crash happened and what the other frames were. We can report every single local variable that was there. We can report how much time was spent that we can get from the interpreter state. This sort of flexibility is not available in most other languages. And as a Python programmer, we are kind of used to this, because even if we don't use it ourselves, if you write a Django application and it crashes, the Django debug page comes up and it prints you out all of the states that was there. Like the framework Django depends on having access to this. Same thing with Flask. If there's an exception, it will print out the stack trace. In Flask, you can even execute your own code in an HTML page and figure out more stuff that's there. And that wouldn't be possible if this wasn't exposed. The other thing that sort of is exposed is sys modules, which is nice on the one hand, but it's not so nice for others. Sys modules is whenever you import a module, it's cached in this special attribute called sys modules. And it guarantees that whenever you import this module, every single other thing will see the same version of it. So if you import the CGI module in this part of the application and you import the CGI module in the other part of the application, then they both will see the same one. And the reason they see the same one is because the module is cached in this sys modules attribute. And the downside of this is that everybody expects it to be there. So at any point in time, people started saying that, oh, I have a class called X, it's from module foo. And I can just go sys modules foo, and I find my class in there. Pickle uses this to re-import its stuff. Copyright uses it to make copies of things. People write import functions like this. Import module, module, under, import, under, module, and then they look for it in sys modules. This is exposed interpreter state. You don't have that in many other languages. And the downside of this is obviously that we will never be able to change this now, because everybody expects that this is the case. So there have been many attempts, for instance, to allow multiple versions of the same Python library to load in the same interpreter. And it seems almost impossible to do now, because we would have to make sys modules also have a version identifier or a scope identifier or something else in there, not just a module name. So the upside is we can discover every single module. The downside is we can only ever have one of them at the same time. And because everybody depends on this, and especially Pickle, and you have to imagine that when people pickle out their objects, they are pickled out for eternity. SOAP has a database which is entirely based on pickling objects. If you change Pickle now, you're going to break all the pickles which were ever created. So until Pickle dies, we will never have version submodules, which is disappointing. This is This is a part which is part of the reason why getting rid of the global interpreter lock is hard. Have you ever wondered, probably not, but I have wondered for a long time, why int is a type and a subclass of int is a class? Did anyone wonder why that is the case? You can show hands. No. So I wondered, why is one thing a type, the other thing is a class? Like, how does it make sense? Like, theoretically, making an empty subclass of an integer, why does it make a different thing? And the answer for this turns out to be that, this, by the way, in Python 3 looks a little bit different. I think they both say type or class now, I'm not sure. But they still work the same. The difference is that a type is guaranteed to live always exactly at the same memory location. And a class sits somewhere on the heap. So you have to imagine this like this. The Python interpreter has a lot of internal types, like integers, floats, strings, Unicode object, lists, tuples, and so forth. And one of the things that the interpreter internally has to do, it has to compare them. Like, for instance, you had this example before where you add two numbers together. If you add two numbers together, the interpreter would like to know, are those two exactly integers? So how does it know if a number is exactly an integer? The reason for this is that there's a PyInt type, which is the internal representation of integers, and it's a global variable. And one of the things with global variables is you can only have one of them. So you can't have two PyInt types. And so what the interpreter does is it checks if the type is exactly the memory address of that integer. So what does this mean? Well, it has a very annoying consequence, which is that, imagine this. Imagine you are Nginx, and you would like to use Python as a scripting language. Then what you would like to do is you would like to have, let's say, 4 or 5 threads running, and each of them has an individual Python interpreter running. That's, for instance, how JavaScript works. If you use a browser, each of your tabs might run an independent JavaScript engine. And these engines, they don't share anything. In Python, we can't do that, because if we would run 2 Python interpreters, they would see the same Python type. And this is not a constant. This can change. There's a reference count on it. People could patch their own things on it if they manage to bypass this interface. And this is, I think, the biggest reason why Python was never a language that was embedded in things. Because the interpreter design internally never supported this idea of having multiple interpreters running, which is it's just really disappointing. And I tried to fix this. I tried to go in and change all of those types and go through a level of indirection to make it possible to, for instance, have one thread running with one completely independent interpreter and the second thread running with a completely independent interpreter. And you start going down a rabbit hole of things you can't change because everybody depends on this. So what are the consequences of all of this? The biggest one is we can't get rid of the GIL. Because we have, for instance, only one integer type, and it's shared across everything. And we couldn't, for instance, say we would like to have one thread running here with one interpreter, another thread running here with another interpreter, and they don't share integer types. But also, we expose on the interpreter level reference counts and other things that are in every single C extension. And it's so ingrained in the language that it's just, at this point, something that you can't take away without changing the language. We can't change the internals because the internals have been changed. And as mentioned before, it's really hard to do multi-version libraries now because sysmodules is an exposed interpreter detail. And it just goes on and on with having this like really complex interpreter which shines all the way to the highest part of the language. And it's something that I understand at this point, that Python as a language is just, this is how it works. And we have to live sort of with this history of how the interpreter works. And Python 3 also couldn't really change that. But it's something that maybe as you go in and then discover other languages is something that you wouldn't want to repeat, sort of. It has obviously strong implications on the speed of the interpreter. And on the concurrency that you can have with it. But it's, I would say, in the current state of how we have the language, it's not something that really stops us from doing a lot of the work that we do with it. But we have sort of a ceiling of where it's hard for us to get over. Yeah, and that's sort of what I have here. Hard to parallel, I mentioned, we can't share these static types. Well, we can't separate the static types because they're shared. And we also can't really go more dynamic because the interpreter already has to cheat in certain places. Like, for instance, Ruby can do making addition into a subtraction if it wants, because there is no fast path for integer addition. But in Python, to stay fast, despite all of this complexity, we lost a little bit there. Yeah. I'm sorry I'm rambling through the slides a little bit, because I'm realizing that it's actually very hard to convey this overall message that how the interpreter works internally in a sense that is sort of easy to understand, and what the ramifications are of it. Which is why I would propose, if people have questions to it, feel free to wildly go off what the actual topic of this presentation is. Because I can see that I think it's maybe not as clear what sort of the point of this leakage is and how it affects people's code. Yeah, that's it.
So what you basically, just since you said that it's maybe hard to get the point across, so what's the point actually that you should expose as small a public API as possible, basically? Because that's what's happening basically when you expose all the internals, then people depend on them, and yeah, you can't take it away. That's the problem.
Yeah, so you have to. The correct thing to do for a language is sort of what JavaScript did in many ways, where you keep the public exposed interpreter API very, very small to non-existent, because then people will never get into this sense where they can start abusing it. And with Python, as mentioned, we have this exposed API, and now it's hard to change it. So yeah, it's this idea of having a small public API, best exemplified, I guess, in the interpreter.
And then again, what about the special cases like you illustrated for the addition? I believe there are lots of special cases in the dict implementation. What's the alternative? I mean, if you lose them, then it's slow, right?
So, but that's the thing. I actually agree. I can see why Python got all of this special handling to make it faster, but it did it in a really wrong way. Because if you consider how a computer nowadays works, a lot of the code is fast because it's cached. It's something. It has a very little footprint. It goes over the same amount of memory all the time. It doesn't invalidate caches. So it would be in the interest of the interpreter to keep the hot code paths as small as possible. So for instance, if we would get more data through dictionaries all the time, then we could make the dictionary code as fast as possible, and we are spending more time in the dictionary code than in all of the rest of the interpreter loop. So I think that by reducing the overall footprint of sort of the complexity that goes into one Python object or the operations it exposes, then we could actually be both more dynamic and more flexible as a result, and also faster, because it becomes easier to reason over it, and we have less code that we have to execute all the time. So it has higher chances of being cached. It has higher chances of being correctly predicted. I think the irony in this is that we are less dynamic than Ruby, but we are probably slower per opcode than Ruby is. As a result of this, because it was obviously slow, so people started doing these optimizations for the common cases, but we could have made the uncommon case significantly faster by simplifying it.
Thanks very much, it was insightful.
You sure? That's it then, thanks Armin.